Okay, so thank you for the invitation. My name is Levent. I will briefly talk about my research topic, which is geometric complexity theory. So I'm about to finish my PhD, and the subject of my PhD is more or less related to this topic. So geometric complexity theory is about polynomials and how you compute them. Um, so one framework to study how you compute polynomials is the algebraic circuits. So you can compute a polynomial using an algebraic circuit. An algebraic circuit is just a directed acyclic graph where on the bottom you have variables and constants, and the other nodes, the nodes on the middle, are called operation nodes, and they are labeled either as a product or as a sum. Um, and each operation node takes two of its children and either multiplies them or adds them. And then by iterating through this process, every algebraic circuit computes a polynomial. So for example, here I gave an example of an algebraic circuit. For example, what this computes is, so it multiplies x1 with x2 and 1, they're added, and then in the end, x1, x2, and x2 plus 1 are multiplied together. So this computes a polynomial, and it should be easy to see that like every polynomial has an algebraic circuit which computes it by basically you can just compute every monomial one by one. But that wouldn't be a very good way to compute a polynomial. So the question is like, so which polynomials are computed by how big of an algebraic circuit? So one related computational model is algebraic formulas. In algebraic formulas, you require that every operation node has out degree at most one. So here I wrote out degree 2, but that's a typo. Intermediate operations have out degree 1. So which means every computation you do can be only used once. In a circuit, you can use them as much as you want. Think of it as like a computer, which computes some portion of the problem and saves it into memory. And whenever it's needed, it can call it. But in a formula, you can only use it once. So it just forgets. Whenever it does a computation, immediately it uses it and it forgets about it. And that's a formula. Well, again, it's easy to see that every polynomial also admits an algebraic formula that computes it. But the question is like, how big of an algebraic circuit or a formula do you need to compute a polynomial, which is a measure of complexity, how hard it is to compute the polynomial. So we define the size of an algebraic circuit as the number of operation nodes. So forget about the bottom and all the remaining nodes. The number of nodes it's the size of the algebraic circuit. And we define um, the circuit size of a polynomial as the minimum possible size of a circuit that computes the polynomial, and as the formula size as the minimum size of a formula that computes the polynomial. So the question is, so let's say you have a concrete polynomial in your hand, how big is LF or EF? Okay, so this naturally leads to two complexity classes, VF and VP. In formula, these are polynomials which have small formulas and small circuits respectively. Now let's define it a bit more rigorously. So we define a P family as a family of polynomials whose number of variables and whose degree grows at most polynomially. Okay, so as you know, the computations and algorithms are always about families of problems, not a one concrete problem. You are never interested in if this particular graph is three colorable, but you want, given a family of graphs, can I decide that if it's tree-colorable or not? So again, so we have to think about families of polynomials, not a one concrete polynomial, but a family of polynomials. So examples of like these P families are, for example, iterated matrix multiplication. So you have D matrices, each of them are n by n, and whose entries are different variables. You multiply these three D matrices and take its trace. That's called iterated matrix multiplication. Well, another famous example is determinant. Determinant is you consider an n by n matrix whose entries are variables and take its determinant. That's a polynomial. Its number of variables is n squared. There are n square entries of a polynomial, and its degree is n, right? And you know, like the formula for the determinant. This is how you define the determinant. You sum overall permutations with a signature. In a permanent, maybe you haven't heard about the polynomial that's called a permanent. It's also a very important polynomial. I will talk more about it later. It's just like determinants, very similar to it, but you don't care about the signatures of the permutations. You just ignore it. So these are like P families. So you say that a family is in VF, a variance class VF, if its formula size is polynomially bounded, and you say that it's in VP if its circuit size is polynomially bounded. So these are two classes of polynomials. The first one is the class of polynomials you can efficiently compute with a small formula, or in other words, you can efficiently compute it using parallel computation. And VP is simply the class of polynomials that you can compute efficiently with an algebraic circuit. So VP is the analog of the complex class P in theoretical computer science. So what we know from Strassen in 1973 is that determinant is in VP. That's not immediately obvious because the way I define the determinant, it's a sum over n factorial things. So if you would use that like Laplace expansion, then that's not a good way to compute a determinant. That would lead to an n factorial sums. That's not a good idea, and it doesn't lead to a small circuit size. But efficiently, essentially what you can do is um, Gaussian elimination. Now, Gaussian elimination requires division, but you can get rid of the division. This is every a circuit with division can be reduced to a circuit without division. So essentially what you can do is Gaussian elimination, which implies that determinant has a small circuit size. Okay, so the determinant is in VP. All right, but what we don't know is if the determinant has a small formula size, and that's an open problem, wide open. If you want to try it, go for it. That it will be fun. So can you compute the determinant with a small formula instead of a small circuit? So you can only use one intermediate computation only once, not twice, okay? So another class is VNP. So that will be the algebraic analog of the NP. And the VNP is defined in a bit different way. So these are all polynomials who are given explicitly, okay? This is the definition, but let's ignore it for the moment. I will give a different definition. A family of polynomials is in VNP if its coefficients can be computed efficiently. Not the polynomial itself, but every coefficient can be computed efficiently. This is not equivalent to computing the polynomial, right? Because it might be possible that it has many, many monomials. And even if you can compute each coefficient efficiently, it doesn't mean that you can compute the polynomial efficiently. So these are the class. This is the class VNP, and it is like the algebraic analog of the class NP. Okay. So one famous polynomial is in VNP is the permanent polynomial, which I just defined. That's a result by Valiant. So this is essentially what we know about these complexity classes. So VF is a subset of VP because every formula is a circuit. That's immediate. And VP is a subset of VNP, which is again essentially by definition. So these are essential by definition. But we don't know if any of these are different. And this is the conjecture, more or less. So the Valiant's hypothesis, Valiant conjecture that VP and VNP are different. Okay. So this is the algebraic analog of P is not NP conjecture. And it is wide open. So this is the conjecture. But what we know, like as I said, so these circuits and formulas, they compute polynomials with coefficients in a field. So this question may depend on the field, right? Maybe with every field, the answer might be different. Well, at least what we know is that it only depends on the characteristic of the field. So you only need to consider the prime fields to solve this conjecture, like F2, F3, like, or maybe Q, like rational numbers. So if you can separate them over rational numbers, you separate them over all fields of characteristic 0, for example. Great. So now an important concept in complexity theory is that of a reduction and complete problems. So again, these classes have complete problems, which is nice. So we call that the polynomial f is a reduction of the polynomial g if you replace the variables in G by numbers or variables of F, then you get F. Okay, so there is an assignment to each variable of G. Either you put a number, evaluate it a number, or evaluate it at a variable of F, and then you get F. If you can do that, you say that G, so there's a reduction from G to F, from F to G, sorry, apologies, from F to G, all right? So, and then we say that a family of polynomials is complete in a class if every other family reduces to that family. Okay. So it's not clear that if there is a complete problem in any of these classes. So what we know is that the iteration matrix multiplication of 3 by 3 matrices is complete in VF. So it's the hardest problem in VF. What we don't know, it's an open question. We don't know if determinant is VP complete. If it's complete in the class of polynomials that has small circuit size. We don't know if it's complete or not. We know that it's complete in a smaller class, but I didn't define it and I will not talk about it.
The
And
time is up. Can we conclude?
all right, I'm about to finish. Okay, just one more minute. So what
Okay.
Valiant proved that the permanent is VNP complete, which is the beginning of this whole geometric complexity theory. And it implies that you only need to consider the permanent. And so this reduces the whole problem to this question of permanent versus determinant. So you have these two polynomials, which is determinant and permanent. So one of them, determinant, it appears everywhere in linear algebra. It counts the number of spanning trees in a graph, and it is the Alexander polynomial in knot theory. I know that like Jeren will talk about it. That's why I put this here. Permanent, on the other hand, counts everything because it's VNP complete. Every counting problem can be reduced to permanent, and it computes the Jones polynomial as opposed to Alexander polynomial. So one of them is easy and the other one is hard, conjectured to be hard. And this is the question that I'm interested in. So the question is this permanent versus determinant. Can you reduce the computation of permanent to the computation of determinant? So the conjecture is no, you cannot reduce it because it should be hard, but proving it is somewhat of a challenge. All right. Thank you.